Hello, I'm Mrs. Arti Fadke from KG Somaya College of Engineering. This is a screencast created for implementing finite state machines using VHDL as a programming language. What we will see in this is fundamentals of state machines. We will also see some features of VHDL which are typically used in implementation of finite state machines and some sample programs where finite state machine is implemented using VHDL. What are state machines? We all have learned that state machines are the machines where the outputs are not only dependent on the inputs but also the history of the machine or the state of the machine. The state of the machine is typically created by a memory element in the circuit. And the state machine is very well described or represented by a state diagram. We have also learned that there are two types of state machines which are known as Moore machine and Milli machine. The fundamental difference between the two is, in case of Moore machines, the output is dependent only on the present state, whereas in case of Milli machine, the output depends on the present state as well as on the present inputs. If we are representing a typical application using Milli machine, the number of states required are typically lesser than that compared to Moore machine. The block diagram for Milli machine and Moore machine is shown over here. We are familiar to this. There is a combinational logic which creates excitation for the memory element from the inputs and the present state. The state change will happen with reference to the clock which comes to the flip-flops, and the output is created with again a combinational logic which depends on the state of the machine and the inputs. Now this is a typical block diagram for a Milli machine. The difference in Moore machine is the output combinational logic depends only on the state and not on the inputs. Importantly, we should notice the feedback going from the memory elements to the next state logic, which is a combinational circuit. Now, these kind of block diagrams can also be represented in two ways. What we have done is we have combined the combinational logic and the sequential logic. Fundamentally, it represents the same thing. Two blocks of combinational logic here are combined into one combinational logic in this diagram, that's all. But why are we doing this? Because this representation is very useful when it comes to implementing a state machine in VHDL. In VHDL, when we are representing a state machine, what we will be doing is we will be writing two processes, one for the combinational part of the circuit and the other for the sequential process. Either we can write two different processes or we can even combine these parts into one process. We will see both the implementations. In implementing a state diagram, it is very important to represent all the states in the state diagram, and hence we are using a very specific data type known as enumerated data type. Enumerated data type is user defined data type in which the elements which the user defines are the only elements in that data type. As a result, if I'm defining something like type, the name of the data type I'm giving as states. And the elements which will be there in my data type are named as idle, reset, state 1, state 2 and error. These are typically state names which may appear in my state diagram. Once I define this kind of a data type, I can create signals of the type states. For example, I'm declaring something like a signals PS and NS, representatives of present state and next state, which are of the type states, which also means that these signals PS and NS will take values only in this set: idle, reset, state 1, state 2 or error. Now we will see how finite state machines can be implemented in VHDL by writing two separate processes, one for combinational part of the circuit where it will generate the next state and the output function, and the other process which will synchronize the next state assignment with the clock. As we can see here, the process which is combinational process is taking inputs as present state and the number of inputs. So it is actually generating the next state and the output, which is going to be a function of the present state and the inputs. Now in case of Milli machine, the output is also function of present state and inputs. What typically we will do in this process is we will write a case statement for the present state, and for each value of the present state we will check the inputs and assign the value of the next state and the outputs for that particular combination. And this is what exactly is being described in any state diagram. What the state diagram indicates is the transition from one state to the other state on occurrence of some input conditions. So what we check there is what is the current state, then what we check is what is the value of the input, and depending on the current state and the value of the input, we assign what will be the next state. So that is what is precisely done. Case present state is when the present state is S idle, you're checking the input condition. If it is 1, then you're giving next state some value. If not, then you're checking another input and things like that. So this is a way in which we will be creating next state and the output values in this process. Once this combinational circuit is producing the next state values and the outputs, these next state values become the present state values on occurrence of the clock, and this will be the clock process. So this is yet another process which is sensitive to clock and reset if in case reset is there in the circuit. All that this process is doing is it is assigning a value to the present state depending on reset or clock conditions. On reset, of course, it is giving a default value. Otherwise, on every clock edge, it is assigning the next state value to the present state. And as soon as the present state changes, the combinational logic or the combinational process will recalculate the value of next state and the outputs. And this is how these two processes are linked or dependent on each other. Now let's look at a particular example of FSM. This is a sequence detector which is detecting 1010 sequence, and we are trying to create a Milli machine. We know very well that in these kind of sequence detector there is one input on which the serial data is coming in and one output which will create a pulse when such a sequence is generated. The state diagram indicates that we have considered 1010 non-overlapping sequence, and as a result the state will keep changing from S0 to S1 on occurrence of 1, S1 to S2 on occurrence of 0, S2 to S3 on occurrence of 1, and on occurrence of 0 it will come back to S0 but with the output 1. So this is a state diagram typically representing sequence detector 1010. What we will be doing is in the combinational process we will be writing exactly this description, and in the sequential process which is dependent on clock we will be assigning next state to present state. So this is a part of the VHDL code. Of course, the library declaration and the usage of packages. The entity, as I said, there is clock and X as the input and Y as the output. Architecture essentially describes enumerated data type. I have named it as my state, and signals PS and NS which are of my state representing present state and next state. YS is a output related signal created. So one process which is dependent on clock is just assigning NS value to PS, and that's all is the sequential process doing. Whereas the process which is dependent on input and present state is considering K statement of PS and will consider all the values of PS, namely S0, S1, S2 and S3. In each case, it is checking X input and just translating what is given in the state diagram, assigning next state value and assigning output value accordingly. Please note that for every state such a sequence is written, and not only that, for completing the case statement when others null statement is also written. At the end of the process, YS is a signal creating the output which is assigned to the output, and this is how we have ended the FSM architecture. When we write it in Quartus and compile, Quartus, like RTL, it also shows the state diagram representation of the code that you have written. Here we can see the state diagram representation of the code which we had written. And after writing a test bench, this is a simulation which shows that when the sequence 1, 0, 1, 0 appears, the output goes to high. Otherwise, for random values of ones and zeros, the output is not high. So this is how we can write the code, write the test bench and simulate the circuit. This is yet another way of implementation of finite state machines, where all that what we have done is we have combined both the parts of the earlier course. And as a result, my process is sensitive to clock and reset and not sensitive to present state or the inputs. But what I'm doing inside is under the clock tick event, I'm writing similar thing like a case statement for states, and calculation of next state is directly done here in the same one process. Of course, when it is a combined process for a small or trivial problems, it will be a easier way of writing state machines. But for complex problems, it may be better for understanding to write separate processes. Here there is a single process which generates the output as well as the next state. The outputs are registered because the outputs are assigned under the clock tick event, and hence only with the rising edge of the clock the outputs are assigned. Of course, since it's a complex process, it generates slightly more logic than the separate processes, and hence writing two processes may be a preferred version for implementing finite state machines. These are some additional practice problems which will also be given on Moodle. Thank you.